Welcome to Lecture 15 of Electrical Engineering 525. In this lecture, we'll cover actually only one problem, but it has 4 parts. And the test problem for this lecture will be very similar to this problem 6.7-2, so definitely pay close attention. Okay, so this problem says a short dipole is a quarter wavelength above a perfect ground plane. Use simple array theory for the dipole and its image to obtain polar plot sketches of the E and H plane patterns when the dipole is oriented A in the vertical direction and B in the horizontal direction. So altogether, there are going to be 4 things that we want to calculate here. The E-plane pattern and H-plane pattern for a vertical dipole above a ground plane, and the E-plane pattern and H-plane pattern for a horizontal dipole above the ground plane. So altogether, 4 complete patterns, 4 total patterns that we want to compute. So first we'll compute the E and H plane patterns for the vertical dipole. And we begin with a picture to make sure we understand exactly what the situation is here. Here is your ground plane. We'll call this the X direction. This is the Z direction. This little arrow here represents the short dipole, and it is a vertical dipole in this first case, so it's pointing up, perpendicular to the ground plane. And finally, the dipole is, as given in the problem, it's a quarter wavelength above the ground plane. Well, the first step in trying to analyze this problem is to realize that since we have an infinite and perfectly conducting ground plane here, we can use image theory to significantly simplify this problem. So that's what we will do. We will take the ground plane away and replace it by this dashed line, and then place another dipole, another vertical dipole, an equal distance below the dashed line. And notice that this vertical dipole is pointing in the same direction as the original vertical dipole. That is, it's pointing up and not down. And remember that that's the way we do image theory for an electric current. The image of an electric current in a perfectly conducting plane, the vertical component will be the same for the image. The horizontal component will be reversed. So this is a purely vertical line current source here, and so its image will look exactly like it. And for this problem, by image theory, we know that for this problem, the fields in the region Z is greater than 0, which is what we're interested in, or will be the same as in this original problem up here. Okay, so now that we have this equivalent problem, how do we solve this? Well, as the problem statement hinted, you will now use array theory, because this is simply an array of 2 short dipoles along the z-axis, and both of those dipoles are z-directed, and one is at z equals positive lambda over 4, and the other one is at negative lambda over 4. So let's proceed with our analysis. When we use this array theory, the idea is that we want to find an element pattern and then the array factor and multiply those together to get the complete pattern for the array. So that's the idea that we will be following as we proceed. Now, we have a good idea of what our problem looks like now, and recall that we want both the E-plane and the H-plane patterns. So let's first start with making sure we understand what the E-plane and the H-plane are. Well, in this problem where we have two vertical dipoles, the electric field will have a radial component and a theta component. If theta is the angle measured with respect to the z-axis, then E could have a radial component straight out from the origin, or it could have a theta component along this angle measured with respect to the positive z-axis. But it won't have any phi component around the z-axis. So we conclude then that the E-plane, for the E-plane, we can use any phi equals constant plane. On the other hand, the H field in this case, with these two vertical dipoles, we know that each one will have an H field that tends to circulate around the dipole. So in this case, the H field will have a phi component, but no radial or theta components. So the H plane we will take to be the XY plane, the plane that is in between, exactly in the middle between these two dipoles. So that is summarized here. Just to read it, note that E has only a theta component. As I said, it actually, now not the far field E. The far field E will not have an R component, but for the near field, E could have a R component and a theta component. But in the far field, E has only a theta component, and H has only a phi component. And so the E-plane can be taken to be any phi equals constant plane, so we will take it to be the plane phi equals 0, which is, of course, the XZ plane. And since H has only a phi component, the H plane is the XY plane. So let's find the pattern in the E plane first, the XZ plane, and then we'll go for the H plane pattern. Okay, so for the E plane, or in other words, the pattern in the XZ plane, which is the plane that we actually have drawn up here. We want the pattern in this plane. Well, the individual, again, remember, the idea of array theory is that you will find the pattern for an element and then multiply that by the array factor to get the complete pattern. Okay, so the elements here are the short dipoles. Each one, they're the same, so the element is a single short dipole in the z direction. And that's repeated here. The element pattern, the element is a z-directed short dipole. The pattern for this is, and we've seen this in a few of our problems, the pattern for this is sine theta. And by the way, that is true even if this z-directed dipole were infinitesimal. In fact, it's true for any z-directed dipole that is electrically short. Okay? So that's the element pattern, simply sine theta. Now, what about the array pattern? Well, the array factor we have learned before in a case like this where we have one element at minus lambda over 4 and another one at positive lambda over 4, and they have the same magnitude of 1, then we get that the array factor is 1 e to the minus j beta lambda over 4 cosine theta plus 1 e to the positive j beta lambda over 4 cosine theta, which from the Euler formula, one of the Euler formulas, is 2 cosine of beta lambda over 4 cosine theta. That is the array factor. And then the normalized array factor is going to, we divide this by 2 and we take the absolute value just to make sure that we get a positive number. And so we'll get the absolute value of cosine of beta lambda over 4 cosine theta. But beta is 2 pi over lambda, so this becomes absolute value of cosine 2 pi over lambda, lambda over 4 cosine theta. The lambdas cancel, 2 cancels, partially cancels with 4, and we're left with the absolute value of the cosine of pi over 2 cosine of theta. Again, f of theta is the absolute value of cosine of pi over 2 cosine theta. So now we are ready to draw our plots and find the complete pattern in the E-plane. This first plot represents the element pattern sine theta. Let's see here. Yes, sorry for the delay there. Okay, the first pattern here is the element pattern, which is sine theta. Now remember, theta is measured with respect to the z-axis. So you can see that here, oh, and by the way, on all of these polar plots, one way that you can start is to draw a circle of radius 1. So that's what we've done in each case, and then we fill in the plot. Now, actually, on your test, in case I forget to mention it when I describe the test at the end of this lecture, but in the test, I did not draw these circles of radius 1 to begin with. I just drew the patterns. But drawing to begin by drawing the circle of radius 1 is a useful thing to do, because you know that the total pattern, since it's normalized, the total pattern should touch the that circle at some point and should not go outside of the circle. So it's sort of useful then to have these circles. But anyway, so sine of theta will look like this, because at theta equals 0, of course, sine of 0 is 0. So we don't, at that angle, we don't go any distance out from the origin. But then as theta increases toward pi over 2, the sine gets larger and larger, and we can see that for different angles, we're going farther and farther out from the radius until we finally get to sine of pi over 2, which is 1. So this is where it touches that circle of radius 1. And of course, over here, the same values of theta. So we have just an, the reflection, you might think of it as the reflection of this in the z-axis. There's no need for us to compute the pattern down here where z is less than 0, because remember, that's where the ground plane was originally. So we're only interested in the pattern in the region z greater than 0. So again, this is the element pattern sine theta. Now, what about the array pattern? Well, this f of theta is the normalized array factor, and that's what we mean here. And you can see that it has a very similar shape. When theta is equal to 0, we would have cosine of 0 is 1 times pi over 2 is pi over 2, and cosine of pi over 2 is 0. So we get 0 at the angle of 0, but when we come to pi over 2, okay, cosine of pi over 2 is 0, 0 times pi over 2 is 0, and the cosine of 0 is 1. So we're out when we get to theta equals pi over 2, the magnitude of this will be 1. And in between there, for values of theta, between 0 and pi over 2, we know that the cosine of theta will always be positive in that region, and so we'll have some positive number, and of course it'll also be less than 1 until we get to pi over 2. So here we will have some positive number less than 1 multiplying pi over 2, and then we'll be taking the cosine of that, and so we will get positive numbers here. In between 0 and 1, we get, again, 0 when this angle is 0, because we get a 1 here times pi over 2, and cosine of pi over 2 is 0. But by the time we get to theta equals pi over 2, then we get 0 here, times that is 0, and cosine of 0 is 1. So this would be our array, a normalized array factor, and it looks quite similar to the element pattern. And when we multiply these two things together, remember now that for each of these, the distances from the origin will always be less than 1, except at this point, at theta equals pi over 2 on either side. So since that's the case, when we multiply, like if we come to some angle here and we get a number, we'll get a number less than 1. Come to that same angle over here, and we'll get a number less than 1. So when we multiply a number less than 1 times a number less than 1, we'll get even a smaller number. And so the net effect of that is that for all angles in between 0 and pi over 2, we're going to get smaller numbers in this total graph than we do in either one of these graphs. However, of course, at theta equals 0, we get 0 in all the cases, and at theta equals pi over 2, we get 1 in all the cases. So the net effect of that is to make this graph look, the beams in this graph will be narrower than the beams in either of these two graphs. But the idea here is, here's our element pattern, here's our normalized array factor, we multiply them together, and here is our total pattern in the E-plane. And again, that's for the vertical dipole above the ground plane. Now, how about for the H-pattern? Well, remember, H-plane pattern. Remember that we said that the H-plane is the XY plane. And for a z-directed dipole, the pattern in the XY plane is isotropic. That is, it doesn't vary in the XY plane. It's not a function of phi. And the same is true for the array factor in the XY plane for elements that are distributed along the z-axis. So if the element pattern is isotropic and the array factor is isotropic, then the complete pattern is isotropic. And if you wanted to draw graphs, we just get our circles of radius 1 in each case, because again, the pattern is independent of phi. The element pattern is independent of phi, the array factor is independent of phi, so the complete pattern is independent of phi. And if you go back and again look at the picture we're talking about, I don't think this is too surprising that if we go around the z-axis, as long as we maintain a constant distance around the z-axis, the field from these two vertical dipoles is not going to change. So that concludes what we get for the vertical dipole case. And now let's go to the slightly more interesting horizontal dipole case. So again, we have here a horizontal dipole, and it is short. It's a distance lambda over 4 above this perfect ground plane. And here again is the z-axis, and here is the x-axis. So using image theory again, here is our equivalent problem, of course, for the fields in the region z is greater than 0. So here's our equivalent problem, and notice that in this case, since the current is completely horizontal, the image is the negative of the original current, because the horizontal component gets flipped. And since this is an entirely horizontal current, then all of it gets flipped in this case. Now we have to decide what the E-plane and H-plane are for this problem. Well, in this problem, in the electric field in the far field will have a theta component, or as I put here, it will have X and Z components, but it will not have any Y component. And in the far field, H could have Y and Z components, but it will have no X component. So as a result of that, the E-plane is the XZ plane and the H-plane is the YZ plane. So the E-plane is the same as it was for the vertical dipole, but our definition of the H-plane has now changed. It's no longer the XY plane, it is the YZ plane. So again, we will start with the E-plane pattern. Now, we learned before that for a Z-directed dipole, the element pattern was sine of theta. Well, now our element is a horizontal dipole rather than a vertical dipole. Well, if you just think of treating now the Z-axis, treating the X-axis as the Z-axis, then you can see that the element pattern now, instead of sine theta, will become sine of 90 minus theta. And again, we need to take the absolute value. So we have the absolute value of sine of 90 minus theta, which will be, of course, absolute value of cosine theta. So that's our element pattern in this case. Now, what about the array factor? Well, we get the array factor just as we did before, but we need to be careful now because we need to remember that the amplitude at negative lambda over 4 is negative 1, while the amplitude at positive lambda over 4 is positive 1. So we have minus e to the minus j beta lambda over 4 cosine theta plus 1 e to the positive j beta lambda over 4 cosine theta. And again, going to one of the Euler formulas, we see that that is 2j sine of beta lambda over 4 cosine theta. And so the normalized array factor will be the absolute value of sine beta lambda over 4 cosine theta, which is sine of 2 pi over lambda over 4 cosine theta, which after we cancel the lambdas and cancel 2, we will get, oh, I love it when it does this. Now, so we get absolute value of the sine of pi over 2 cosine theta. And that, again, is the normalized array factor. So now, when we put that all together, we will get, here is the element pattern. This is cosine of theta. Notice that when theta is equal to 0, we go up to 1, and we slowly get smaller until we get to theta equals pi over 2, and of course cosine of pi over 2 is 0. So that explains this graph. And then here is our array factor, which looks quite similar. It is the absolute value of sine of pi over 2 cosine theta. When we start off at theta equals 0, cosine of 0 is 1, 1 times pi over 2 is pi over 2, and sine of pi over 2 is 1. So at theta equals 0, we have 1. But when we get to pi over 2, cosine of pi over 2 is 0, 0 times pi over 2 is 0, and sine of 0 is 0. So we get this. And once again, then when we multiply these two things together, we get a graph that looks similar, but it's narrower. We get a narrower beam, but a beam that otherwise looks similar to these two. And so this will be the complete pattern in the E field for the horizontal dipole. And now the last thing we need to do is to find the complete pattern in the H-plane. And remember, the H-plane is the YZ plane this time. We need the complete pattern in the YZ plane for the horizontal dipole. And before I reveal how to do this, I would strongly encourage you to try to stop the video now and do this on your own, and then come back to the video and see if you were right. Okay, so now for the H-plane pattern. Well, the element, as we've said, is a short x-directed dipole, and we're looking for the pattern in the YZ plane. Well, since the dipole is perpendicular to that plane, its pattern in the YZ plane is isotropic, similar to what we had above for the vertical dipole. So we have, when we were looking for the vertical dipole, we were looking in the XY plane. Now we're looking in the YZ plane for a horizontal dipole, but still, we conclude that the pattern is isotropic. So the element pattern in this case is isotropic. What about the array factor? Well, in our problem before with the vertical dipole, remember that the E-plane for the vertical dipole, the E-plane was any plane phi equals constant. We took it to be the XZ plane, but it could have been also the XY plane, the YZ plane. Any plane where phi is constant would have served equally well as the E plane. And then the H plane was the XY plane, which was a totally different plane in the sense that the XY plane, for this problem, the XY plane doesn't contain any of the dipoles. We have one dipole above the XY plane and one dipole below the XY plane. So when we looked in our first problem for the vertical dipole, let's go back up here again for a second. For the vertical dipole, when we looked in the E plane, we got this array factor, but when we looked in the H plane, we got this array factor. And once again, the E plane could have been any phi equals constant plane. In any of the phi equals constant planes, the array factor would have looked like this. All of those phi equal constant planes contain the two dipoles. The H plane, or the XY plane, does not contain the dipoles. There's one dipole above the XY plane and one dipole under it. So the array factor is different. But for the horizontal case, like this, okay, now the E plane is this XZ plane, and the H plane is the YZ plane. But both of those planes look the same as far as the dipole locations are concerned. That is, these two dipoles are located along the z-axis. We're not worrying for the moment. When we're looking at the array factor, we don't worry about how they're directed. We're just concerned with where they are located. Both of them are located on the z-axis, and the z-axis is part of the xz plane, and it's also part of the yz plane. So in this case, for the horizontal dipole, the array factor will be exactly the same for the E plane and the H plane. So we see that right here. See, The array factor here is exactly the same as the array factor here. Again, the array factor is same for the E-plane and the H-plane in the case of the horizontal dipole. But now the element factor is different in those two, because for an x-directed, in other words, a horizontal dipole, when we look in the E-plane, in the XZ plane, we get this cosine theta variation, but in the YZ plane, we get an isotropic pattern. And so finally, to wrap this up, when we multiply this isotropic pattern times this, of course, since this is equal to 1 everywhere, we'll just get back the same pattern here. This is exactly the same as the array factor. And so this would be the complete pattern for the horizontal dipole. This is the complete pattern in the H-plane. And that completes lecture 15. So now let me explain to you what you want to do for the test for this lecture. It is going to be exactly the same problem, except that now the dipole, instead of being a quarter wavelength above the ground plane, it will be a half wavelength above the ground plane. That's the only difference. It's still a short dipole. And so to be specific then, in problem 15.1, you want to find the E-plane pattern for a vertical dipole. That is, of course, half a wavelength above the ground plane. In 15.2, you want the H-plane pattern for that same vertical dipole. In 15.3, you want the E-plane pattern for a horizontal dipole, half a wavelength above the ground plane. And in 15.4, you want the H-plane pattern for a horizontal dipole that is half wavelength above the ground plane. And the four choices for the patterns that you're given in each case are all the same. And as mentioned before, in each one you should, I didn't put the circle of unit radius around these, but in each case you can assume that the maximum distance for the plot, the maximum distance from the origin is 1. So for instance, in this one, this would be 1 here, and this would be a distance of 1 down here. This is a distance of 1, and this is a distance of 1. In this case, it's all a distance of 1. And then in this case, this is a distance of 1, and this is a distance of 1. And the last thing I want to say is that you see that plots A and D are similar, but D is, my drawing is not perfect, but I think the drawing does convey my intention, which is that the plot in D, these beams are supposed to be narrower than the beams in A. I believe that will be enough information then for you to do all 4 of these problems. And good luck.